Have you ever wondered how your camera, let's say, automatically detect faces, or how medical images counts cells in blood samples? So this called, let's see, blob detection. So today we are, let's see, going to dive into blob detection using Laplacian of Gaussian. And by the way, Laplacian for edge detection is already explained in a more details with real, let's see, with numerical examples. So if you are not familiar with Laplacian, please refer to the previous videos on the edge detection. Okay, so let's go to the next slide. So what are the blobs? So imagine you are looking at a white piece of paper, and someone drop a few drops of ink on it. This ink spots, let's say, consider as blobs. They are, let's say, just circular or around regions that look different from their surroundings. So this is how to detect, let's see, what are the blobs. So some samples of the blobs, as you can see here, is blood cells in the medical images, stars in the astronomical images, or maybe in the sky, bubbles in liquid, and many other, let's see, samples. And in this example here, we have, let's see, five image with 5 by 5 image pixels. So just to make let's see, a real example, I mean simple example. So now let's go to the Laplacian. So why we need to use Laplacian of Gaussian and not only Laplacian or maybe Gaussian? This we will see how to why. So for the blob detection, we need two steps. Uh, Gaussian smoothing, which is removing noise and small details. Sometimes when you have an image and you would like to detect edges or corners without removing the noises, you will have many images that are not needed to be, let's see, considered as edges or corners. And after removing the noises, it will make the blob detection more robust. And the next step is find rapid intensity changes. So as we have already seen in the edge detection or corner detection, when we have some changes in the intensity, we have seen this is an edge detection or maybe corner detection. And why we combine Laplacian and Gaussian? As you can see, Gaussian alone is smooth everything, so we will lose some details. And Laplacian is a too sensitive to a noise. If you apply, if you use only Laplacian, we will have many, let's see, false positive edges. To combine both Laplacian and Gaussian, it's a perfect balance, finding a significant blobs, and while of course ignoring the noises. The next one is a Gaussian filter. So now uh, this formula, it's somehow you can see the formula, it's too let's say complex, but we will try to make it small, free simple. So this is a Gaussian. If you have any image and you would like to apply this filter, or let's say this formula on it, so let me just show you this image here, and you can see this image. It's trying to calculate, let's say we're trying to make apply this formula on a small piece of images, piece of regions, let's say 3 by 3, and the center pixel will be 0 0. And if you go to this direction, it means x will be the same, I mean, y will be the same, but x it's minus one. We shift x to one. I mean minus one, and this is the opposite direction, 0 and 1. And here is y is we are minus one. We are in this position, decreasing the zero. I mean minus one, and here we are one. So now let's assume this 0 by 0. You will apply this formula here, and you will replace zero, I mean y and x with 0 0 0, and you will get a final, let's see, a value for this, and you will put it here. And what about the standard deviation, or this sigma here? and the sigma could be, so you can see here, small sigma less blur, more detail preserve, and more sigma is more blur and only large features remain. And it's, let's see, it's up to you if you would like to use, or you can try to use several Gaussian, different sigma values. So after calculating this, you can see we have, if we calculate, apply this, these values here, with this formula here, we will get these simple, let's see, filter, or let's see, normalized Gaussian distribution. And this could be for a small region, and you can apply it for the whole image when you select, let's see, we convolute this image on the kernel on the image. And we have, if you are not familiar with edge detection, I have already uploaded 3 videos on edge detection, Canny and Laplacian, also filters, also Gaussian. So you can see how the filter is convoluted to the image. So after assuming this, we have the Laplacian. If you see also the Laplacian, we have seen how we get this filter here. So last time I showed you how we get we got this filter here. So this filter here, we will try to now to detect the blobs, and you can see positive blobs. Positive values is dark blobs, and negative values is bright blobs, and zero it's a uniform area, or maybe no blobs there. So assume that we have this part of the image 3 by 3 taken from any image. Let's see 3 by 3, and assume that we have this image here. This is rectangle here, and we will start from scanning the image from here and multiply by the kernel. Hopefully you are familiar with this. As I said, if not, if this is not clear, please have a look in the previous videos and come back and return back to this. You will understand it 100%. So we have, let's see, this image here, and we'll apply a filter three. We'll take 3 by 3 images in this direction. After finishing this direction, we will go to this direction until completing the image. So now let's assume this is taken from one image 3 by 3, and apply this configure this filter or Laplacian kernel, and we will get this result 160. If you see 10 times 0, it's 0. Then 10 times minus 1 plus 10 times 0 plus 10 times minus 1 plus 50 times 4, and etc. And after that we have 160. And if you see, it's a strong positive response. This is a brightness blob. If you see, it's a bright. It's a bright, and he is a dark. Sorry for this. And let's go back to this. This is the same of the Gaussian. And after applying this Gaussian, we will see, for instance, this is with standard diffusion 1.4, and we will see calculating this, and we will see what is the result. So if you see here, we have the original image, and we will focusing on this pixel here, which is, I think, 3 3 3. It's x 3 in x direction and y 3. So you can see 0 1 2 3, and here 0 1 2 3, and this is the center pixel. This 3 and 3, so the 20, and we will multiply this, and we will see what is the result. Here's the result is 20, and if we apply it now for the 1 1 1 1 1, it means 0 1 and 0 1. So this is the center pixel here. This is the intersection of 1 1. So we will see, we will take this 3 by 3 image and apply it. It will be 0. So this is how to detect the blobs. And now we will see, if you see this, how to get the radius of the blobs. And the radius of the blobs is can be detected, found by sigma times square root of 2. The sigma here, sometimes we have used 1 2 3, and And what if I want? And so, for instance, here is some examples. If you are using 1 sigma as 1, so then we will try to multiply this times this. The result will be 1.41. So this is 1.41 pixels. So this is the radius of the blob. So if we have detected any blob, let's see, for instance, I can't see anything. If we detect a blob, so we can see calculate. The radius will be 1.4 pixel. It means in all direction we can see this is a blob, and if we increase this, it will of course increase the blob radius, and etc. So this is the how we detect the blobs, and the complete algorithm. Sorry, let me just give me 1 second. Okay, now let's let's put let's put everything, let's see, together into our blob catching, let's see, machine. So step one, we build our scale space. Think of it as a creating multiple versions of our images, each optimized for different blob size. We have seen, for instance, in the previous one, we have seen this different scale. And next, we hunt for, let's say, local maxima. These are our blob candidates, saying, let's see, bake me, for instance, if it's greater than the specific threshold, we can see this is a blob. After that, we set our standard, let's say, high and high, with a threshold only a strongest response could be, let's see, used. And it's like having a semantic approach to finding all hidden treasure in the image. And the next one here. So before we wrap up, let me share some inside, let's say, secret. If you want lighting fast performance, use separable filters. And if you want, if you, let's see, false alarm or false positive, if you're applying, let's see, edge detection and you need to reduce the false positive means you detect some edges, but indeed they are not edges. This is called false positive, or let's say false alarm. And you have to take care of the threshold, and miss maybe some let's see, missing, let's see, blobs. You can reduce or maybe use some more scales. And so for the optimization, yeah, this is we already said. And let's see common, let's see, problems. A problem is too many false detection, solution increase threshold, or sharp verification. If you have, let's see, for many false positive, we can see we need to increase the threshold to remove, or let's say to avoid this false positive. And missing small blobs, we need to small scales, and also reducing the threshold. And I think we have already done. And of course, if you have any question, just drop it in the comment below. And let's say the advantage of this is it's mathematically well founded. I mean, it's easy to even you can implement it yourself. And the limitation is computationally expensive. Only take circle blobs. Yeah, this is one issue. And sensitive to the threshold. For instance, if you have taken some different thresholds, you will have different results. And some applications are cell counting, tumor detection. Sometimes you have medical images, and to detect the it's used also for detecting the tumor, but it's not, let's say, more accuracy. We have to use, let's see, for such applications we have to use deep learning. And also industrial is a defect detection and quality control. Again, this, if you have, let's say, simple images and not, let's say, complex structure, you can use this. But for the anomaly detection or defect detection, quality control, I will recommend you to use, let's say, for instance, anomaly detection or defect detection. By the way, for anomaly detection, I have already implemented really robust. It's not, let's see, fully implemented, but you can see here. Let me just go back. You can see here optimized button based on this repo here, and it's easy to use and also not that hard. So you can see the contributors. I have used acknowledgements. Yeah, so I have added here. So this inspired this work. So you can see. Okay, I think that's it for today, and thanks for watching, and see you next time.